Hello everyone, I am Divyanshu and I have another very interesting topic to discuss with you today. So, in astronomy, there is a very interesting concept called the Goldilocks zone. So, let's imagine a scenario in which you are God. You have already created the sun, you have already created the earth, and now you want to place the earth at a reasonable distance from the sun so that you can then put humans on it. So humans thrive at a certain temperature. If, for example, the Earth had a temperature, mean temperature of say 100 degrees Celsius or 200 degrees Celsius, we'll all burn out, right? So if you place the Earth very close to the sun, we'll all get burnt. On the other hand, if you place the Earth too far, the temperatures might get very cold. Say, for example, minus 100 degrees Celsius. So then what will you do? So if you're God, you have to calculate the precise distance at which you should place here so that the humans neither get too hot nor get too cold and your humans can actually survive very comfortably. So how do you calculate the Goldilocks zone of that? So this zone is called the Goldilocks zone, in which you can place a planet and still have temperatures that are neither too hot nor too cold so that life can thrive on it. So for our solar system, for our sun, only two planets fall in the Goldilocks zone, and those two are Earth and Mars. So Venus is very hot, and planets beyond Mars are again very cold. For example, Neptune is very cold, Saturn is very cold. So because of all these reasons, we want to actually find the accurate distance at which we should place our Earth, so that the temperature at the Earth is nominal for our humans to survive. So can we calculate that? Can we actually calculate? Can we actually precisely put down what distance should I place my Earth from the sun so that the temperature there is maybe 25 degrees Celsius, what our room temperature is. So let's see how we can calculate that distance. So let's start looking at this from our everyday experience. So say for example you have a hot object, for example a piece of coal that is at some temperature T, and you place your hand somewhere near it. You feel the heat that is coming out from this piece of coal, right? So this mode of heat transfer is called radiation. This hot piece of charcoal is actually radiating out heat, and that heat radiation is reaching your hand and warming up your hand. And similarly, there are other experiences also, right? For example, you have food that comes out of your microwave oven. If you place your hand near that food, you will feel some kind of a heat that is being radiated out of that piece of food. So this mode of heat transfer is called heat radiation, and that's how the sun actually warms up all the planets in the solar system. So for example, this is the sun right here. I'm just going to draw it like this. It's the sun. And let's say we have some planet here, some planet over here, and some planet over here. So it's going to radiate out heat to each of these planets, and because of this radiated out heat, all these planets is going to heat up. So that's how any planet gets heated up and reaches a particular temperature. So let's say we now want to place Earth somewhere here, and this Earth basically now gets to some temperature T. It's now going to start radiating out heat on its own, right? Because any hot temperature is going to radiate out heat. So if the Earth gets hot, that itself is going to radiate out some kind of a heat in all directions, in all possible directions like this. So if we place a sun that is heating out our Earth, it's going to get some heat from the sun. This is the radiation that is coming from the sun. It's going to radiate out heat as well, right? And if the heat that it receives is more than what it gives out, then the temperature is going to keep rising. On the other hand, if it gives out more heat as compared to what is coming in from the sun, then it's going to cool down. So it's going to stop is when the amount of heat that is coming in from the sun is exactly equal to the amount of heat that it gives out, right? That's when it's going to reach a particular temperature, and let's say we want to keep that temperature to some 25 degrees Celsius. So like a thermostat, as in you want to make this setting to 25 degrees Celsius, and when that particular object reaches that 25 degrees Celsius, you stop. So if we can calculate the amount of energy that is coming in and the amount of energy that a heated Earth is going to throw out, then we can effectively calculate what is the equilibrium temperature of the planet at a particular distance from the sun. So now how do we do that? There is a law in physics that helps us calculate the amount of energy that a hot object radiates, and that particular law is known as Stephen Boltzmann's law. Stephen Boltzmann's law. What that tells us is that if there is any hot object with some temperature T and some surface area A, then the energy per unit time that it radiates, I'll just call it energy, that is going to be equal to some constant sigma times the temperature raised to power 4th times the area. So as I told, right, the amount of energy that it's going to give out will depend on the temperature it has, right? If it's hotter, it's going to give out more energy, and also if it has more surface area, it's also going to give out more energy, right? So going back to the coal example, if you have a bigger piece of charcoal and you place your hand near that, you're going to feel much hotter, right? Because it has more area, so it radiates out more energy. So that's Stephen Boltzmann law that tells us how much heat a given heated object actually throws out. So if our Earth is at some 300 Kelvin, then it's going to throw out this sigma times T, which is now 300 Kelvin, times the area of the Earth, which is 4 pi times some radius of the Earth square, considering that it's a sphere, right? So that's what it's going to throw out. Now the sun itself, so this heat is coming from this sun, and this sun itself is a hot object with some radius r and some temperature T, right? So again, the Stephen Boltzmann law applies to the sun as well. So the energy that it actually gives out is sigma times T sun to the power 4 times 4 pi r sun squared, right? So that's the energy that it's giving out. But this energy actually, this is the total energy that it's giving out in all directions, and all of it is not going to be received by the Earth, right? Earth is only going to receive a portion of it. So if this is the sun, let's say, and this is the Earth somewhere, and the sun actually, because of being hot, radiates out heat in all directions, in all possible directions like this. So it basically radiates out heat in some sphere of this kind, right? So this is the Earth and this is the sun. There is a sphere of some particular radius, which is the distance between the Earth and the sun. So it's radiating out heat in all directions in this sphere, and Earth is only sitting in a patch here in this sphere. So this total patch has an area of 4 pi times d square, and out of that, the Earth is only, if its radius is r, that this patch of Earth is only pi r Earth square area. So this is the only portion of this total sphere that actually is covered by this Earth. So only this portion, pi r Earth squared divided by 4 pi d square. So this is the portion of the total heat that Earth is going to receive. So basically this is the total energy that the sun is giving out. Actually it's not energy, it's power, but let's just say it's energy, and that multiplied by this factor here. So the pi's cancel out, it's e r Earth squared divided by 4 times d squared. And now if we just equate this with this, so at equilibrium, the energy that the Earth receives, the portion of the sun's energy that the Earth receives, is going to be exactly equal to what the Earth itself is giving out, right? So now if we just equate both of them, we have, let me write this over here, sigma times T sun to the power 4 times pi r sun squared times r Earth squared divided by 4d squared equals sigma times T Earth, which we are taking as 200 Kelvin, squared times 4 pi r Earth squared. So if we just cancel out the common terms, this sigma, for example, gets cancelled, r Earth gets cancelled, these 4 pi's get cancelled. We can calculate this distance d from here. So our role as God is now over. So we get T sun equals root r sun divided by 2d times T Earth. So that's our final relationship, and from there we can calculate d. So if we just plug in these values, we know the temperature of the sun is close to 6000 Kelvin. Exactly speaking, it is 5780 Kelvin. We know the temperature that we want on Earth, that's 300 Kelvin. We know the radius of the sun, and from there if we try to calculate the distance, it comes out to be some 130 million kilometers. So in Hindi that is approximately 10 crores, 13 crores, 10 crore kilometer or 13 crore kilometer. So that's where you're going to finally place Earth if you want humans to survive. So that's it. That's how we make the calculation of where to place Earth if you were to place one. Thank you.